Tonight, we're going to talk about our solar system. 8 planets, some moons, a belt of asteroids, maybe a few comets. Simple, right? Here's what most people don't realize. Almost everything you learned about our solar system in school is outdated, incomplete, or just plain wrong. The solar system we actually inhabit is far stranger, more chaotic, and more violent than the neat diagrams suggest. By the end of tonight, you're going to see our cosmic neighborhood in an entirely different way. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you think you know. You've probably seen countless images of the solar system. 8 planets orbiting in neat, circular paths around a yellow star. Mercury closest to the Sun, then Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, and Neptune. All moving in the same plane, like a spinning disk. All orbiting in the same direction. Stable, orderly, predictable. That's the picture most people carry in their heads. And it's not entirely wrong, but it's dramatically incomplete. The real solar system is messier, more dynamic, and far more interesting than those simplified diagrams suggest. Consider the asteroid belt. Most people imagine it as a dense field of rocks, like the asteroid fields in movies, where spaceships have to dodge and weave between tumbling boulders. That's completely wrong. The asteroid belt is mostly empty space. If you were flying a spacecraft through the asteroid belt, you'd probably never see an asteroid with your naked eye. You'd have to actively search for them with instruments. The asteroids are spread out over such vast distances that the average spacing between them is about 740,000 miles, or about 1.2 million kilometers. That's roughly 3 times the distance between Earth and the Moon. You could fly through the asteroid belt completely at random, and your chances of hitting anything would be essentially 0. NASA has sent multiple spacecraft through the asteroid belt, and none of them have encountered any problems. Pioneer 10 was the first to cross the belt in the early 1970s. Since then, Voyager 1, Voyager 2, Galileo, Cassini, New Horizons, and others have all passed through without incident. Not one has needed to dodge asteroids or navigate carefully around obstacles. They just flew straight through regions calculated to be safe, and those regions were safe because space is overwhelmingly empty, even in the densest parts of the asteroid belt. But here's where it gets interesting. The asteroids that do exist aren't distributed randomly. They're organized into families and groups by gravitational resonances with Jupiter. Jupiter is so massive that its gravity shapes the entire asteroid belt. Certain orbits are stable because they're in resonance with Jupiter's orbit. An asteroid in a 2-to-1 resonance with Jupiter, for example, orbits the Sun exactly twice for every one orbit Jupiter makes. That creates a stable configuration. But other orbits are unstable. Asteroids in certain locations get pulled and tugged by Jupiter's gravity in ways that amplify over millions of years. Eventually, these perturbations become so large that the asteroids get ejected from those orbits entirely. The result is gaps in the asteroid belt called Kirkwood, gaps after the astronomer Daniel Kirkwood, who discovered them in 1866. If you plot the number of asteroids versus their distance from the Sun, you don't see a smooth distribution. You see a distribution with distinct gaps at specific distances. These gaps correspond exactly to orbital resonances with Jupiter. Any asteroid that wanders into these regions gets kicked out by Jupiter's gravitational influence over time. This is one of the first hints that the solar system isn't static. It's dynamic. Objects move, orbits change, and planets like Jupiter actively reshape the structure of the system over millions of years. Now let's talk about the planets themselves. You learned that the planets orbit in roughly circular paths. That's mostly true for the 4 inner rocky planets. Earth's orbit is very close to circular. Venus has the most circular orbit of any planet, with an eccentricity of just 0.0067. That means its orbit is almost a perfect circle. But move beyond the asteroid belt and things get stranger. Jupiter's orbit is slightly elliptical with an eccentricity of 0.0489. That means, at its closest approach to the Sun, called perihelion, Jupiter is about 460 million miles, or about 740 million kilometers, from the Sun. At its farthest point, called aphelion, it's about 507 million miles, or about 816 million kilometers, away. That's a difference of about 47 million miles, or about 76 million kilometers. Not huge compared to Jupiter's average distance, but still significant. Saturn's eccentricity is 0.0539, slightly more elliptical than Jupiter. Uranus is 0.0472, about the same as Jupiter. But then there's Neptune. Neptune has an eccentricity of only 0.0086, making it more circular than any of the other giant planets. You'd expect the outermost planet to have the most elliptical orbit, but it doesn't. Neptune's orbit is oddly circular for its location. Why? We're not entirely sure. It might have to do with how Neptune formed or how it migrated to its current position, which brings us to one of the strangest discoveries about our solar system. The planets haven't always been where they are now. They've moved. This idea is called planetary migration, and it's revolutionized our understanding of how solar systems form and evolve. For most of the 20th century, astronomers assumed that planets formed in their current orbits and stayed there. Jupiter formed at 5.2 astronomical units from the Sun. 1 astronomical unit is Earth's average distance from the Sun, about 93 million miles, or about 150 million kilometers, and it stayed at 5.2 astronomical units forever. Same for all the other planets. But observations of exoplanets, planets around other stars, showed this couldn't be right. Astronomers discovered hot Jupiters, gas giant planets orbiting extremely close to their stars, closer than Mercury orbits our Sun. These planets couldn't have formed where we find them today. Gas giants form in the outer regions of planetary systems where it's cold enough for ice to condense. That's where there's enough solid material to build the massive cores needed to attract huge amounts of gas. Hot Jupiters must have formed farther out and then migrated inward. Somehow, they moved from the outer solar system to orbits that take them skimming just above their star's surface. If migration happens in other solar systems, it probably happened in ours too. This led to the development of the Nice model, named after the French city where it was developed, not because it's nice, although it is a compelling model. The Nice model proposes that the outer planets formed much closer together than they are today. and that they migrated to their current positions through gravitational interactions with the disk of small, icy bodies left over from planet formation. According to this model, in the solar system's early history, about 4 billion years ago, Jupiter, Saturn, Uranus, and Neptune were arranged differently. Jupiter was slightly closer to the Sun than it is now. Saturn was also closer. Uranus and Neptune were much closer to the Sun, possibly inside where Uranus is today. Beyond the planets was a massive disk of icy planetesimals, small bodies made of rock and ice, similar to comets. This disk contained maybe 20 times the mass of Earth, spread across billions of individual objects. As the planets orbited, they gravitationally scattered these planetesimals. Jupiter and Saturn, being the most massive, did most of the scattering. When a planetesimal passed close to a planet, the planet's gravity would change the planetesimal's orbit. Sometimes the planetesimal would be flung inward toward the Sun. Sometimes it would be flung outward. Here's the key point. Every time a planet flings a planetesimal, the planet's orbit changes slightly too. It's Newton's third law applied to orbital mechanics. For every action, there's an equal and opposite reaction. If Jupiter flings a planetesimal outward, Jupiter's orbit moves slightly inward. If it flings one inward, Jupiter moves slightly outward. Over millions of years, with billions of individual scattering events, these small changes add up. The planets migrate. In the Nice model, Jupiter migrated inward slightly. Saturn migrated outward. Eventually, Jupiter and Saturn crossed a orbital resonance, a configuration where their orbital periods had a simple integer ratio. When this happened, their gravitational interaction became much stronger. This triggered what's called the late heavy bombardment. The orbital changes of Jupiter and Saturn destabilized the entire outer solar system. Uranus and Neptune got scattered outward into the disk of planetesimals. As they plowed through this disk, they scattered objects in all directions. Billions of icy bodies were flung inward toward the inner solar system. This created a massive bombardment of the inner planets. Earth, Mars, Venus, and Mercury were pummeled by impacts. The Moon's surface still bears the scars of this bombardment in the form of large impact basins. The late heavy bombardment occurred about 3.9 billion years ago. We know this because the oldest rocks on the Moon date to this time. Before this, the Moon's surface was completely different, probably smoother, with fewer large craters. The bombardment created the heavily cratered surface we see today. On Earth, this bombardment would have been catastrophic for any life that existed. But, ironically, it might have also delivered the water that makes life possible. Many of the impacting objects were comets, essentially dirty snowballs made of ice and rock. When they hit Earth, they brought their water with them. Some scientists think most of Earth's water came from comets delivered during the late heavy bombardment. The Nice model explains several mysteries about the solar system. It explains why Neptune is farther from the Sun than Uranus, even though Neptune is more massive. Normally, you'd expect the more massive planet to be closer in. But if Neptune formed closer to the Sun and was then scattered outward during the migration, ending up beyond Uranus, that would explain their current arrangement. It explains the Kuiper belt, the region of icy objects beyond Neptune. These objects are the survivors of the planetesimal disk, the ones that didn't get scattered by the migrating planets. and it explains the late heavy bombardment, which is recorded in the cratering record of the Moon and probably occurred on all the inner planets. But the nice model is just a model. It's our best current explanation, but it's not proven. There are other models, other possibilities. Some models suggest there was a fifth giant planet that got ejected from the solar system entirely during this chaotic period. Computer simulations show that you can start with 5 giant planets and end up with 4 if one gets flung out by gravitational interactions. Where did this fifth planet go? It's drifting somewhere in interstellar space, a rogue planet with no star, wandering in the darkness between stars. Other models suggest the planets migrated multiple times in different directions before settling into their current orbits. The truth is, we're still figuring this out. Planetary migration is now a fundamental part of our understanding of solar system formation. But the details, exactly when it happened, how fast it happened, which planets moved where, are still being worked out. Now, let's talk about something even stranger. The planet that might exist beyond Neptune. For years, astronomers have noticed something odd about certain objects in the outer solar system. A group of trans-Neptunian objects, objects that orbit beyond Neptune, have orbits that are strangely aligned. Their orbits are highly elliptical, stretched out into long ovals, and these orbits all seem to point in the same direction. The chance of this happening randomly is extremely low. Something about 0.007%, according to one calculation. So, if it's not random, what's causing it? One possibility is that there's another planet out there, a large planet farther from the Sun than Neptune, and its gravity is shepherding these objects into aligned orbits. This hypothetical planet has been called Planet 9, or sometimes Planet X. Not to be confused with Pluto, which was called Planet X before it was discovered and later demoted to dwarf planet status. If Planet 9 exists, it would be unlike any planet we've found in our solar system. Based on the orbits of the objects it's supposedly influencing, Planet 9 would have to be fairly massive, somewhere between 5 and 10 times the mass of Earth. That would make it similar to Uranus and Neptune, which are ice giants with masses about 14 and 17 times Earth's mass, respectively. But Planet 9 would orbit much farther from the Sun. Its average distance might be around 400 to 800 astronomical units. Remember, Neptune orbits at about 30 astronomical units. At 400 astronomical units, Planet 9 would be more than 13 times farther from the Sun than Neptune. Its orbital period would be somewhere between 10,000 and 20,000 years. That's how long it would take to complete one orbit around the Sun. At such a great distance, it would be incredibly faint. Even though it might be several times larger than Earth, it would be so far away and receiving so little sunlight that it would be extremely difficult to detect. Some astronomers have been searching for it for years using powerful telescopes, but so far, no one has found it. That doesn't mean it doesn't exist. The outer solar system is enormous, and Planet 9, if it's there, could be anywhere along its huge orbit. It's like searching for a specific pebble in a football stadium when you don't know which section of the stadium to look in. You know roughly where it might be, but the search area is still vast. Other astronomers are skeptical. They think the aligned orbits could be explained by other mechanisms, perhaps the combined gravitational influence of many smaller objects or observational bias. Meaning we've only discovered the objects with aligned orbits because that's where we've been looking most carefully. The debate continues. Several large-scale sky surveys are currently underway that might settle the question within the next decade. If Planet 9 is there, one of these surveys will probably find it. If they don't find it after searching thoroughly, that would be good evidence that it doesn't exist. But imagine if it does exist. Imagine we discover a fifth giant planet in our solar system, hiding in the darkness beyond Neptune. It would completely change our understanding of the solar system's architecture. It would raise new questions. How did it get there? Did it form where it is now, or did it migrate outward? Could there be other planets even farther out that we haven't detected yet? Now, let's talk about the Sun itself. You probably think of the Sun as a stable, unchanging ball of hot gas. And on human timescales, it is stable. It's been shining with roughly the same brightness for millions of years. But zoom out and look at longer timescales, and the Sun is anything but stable. The Sun is currently about 4.6 billion years old, about halfway through its main sequence lifetime. It formed from a collapsing cloud of gas and dust, and it will continue fusing hydrogen into helium in its core for another 5 billion years or so. But over this time, it's not constant. When the Sun first formed and began nuclear fusion, it was about 70% as bright as it is today. Over billions of years, as helium builds up in the core gets denser and hotter. This causes the fusion rate to increase, which makes the Sun gradually brighter. About 1 billion years from now, the Sun will be about 10% brighter than it is today. That might not sound like much, but it's enough to have catastrophic effects on Earth. The increased energy will evaporate more water from the oceans. Water vapor is a greenhouse gas, so this will cause temperatures to rise even more. This creates a runaway greenhouse effect. More heat means more evaporation, means more water vapor, means more heat. Eventually, all of Earth's oceans will evaporate. The water vapor in the atmosphere will be broken apart by ultraviolet light from the Sun into hydrogen and oxygen. The hydrogen, being light, will escape into space. Earth will lose its water permanently. This will happen in about 1 billion years, maybe 1.5 billion years. Long before the Sun becomes a red giant. So when you hear that the Sun has 5 billion years left, that's true. But Earth doesn't have 5 billion years left as a habitable planet. It has maybe 1 billion years, possibly less. After that, Earth becomes Venus, a scorched, dry world with surface temperatures hot enough to melt lead. Eventually, in about 5 billion years, the Sun will exhaust the hydrogen in its core. Fusion will stop. The core will contract and heat up. This will cause the outer layers to expand enormously. The Sun will become a red giant, swelling to perhaps 100 times its current diameter. It might engulf Mercury and Venus. It might reach Earth's orbit. Even if it doesn't quite reach Earth, our planet will be uninhabitable, a charred cinder orbiting close to the Sun's bloated outer layers. The Sun will remain a red giant for about 1 billion years, fusing helium into carbon and oxygen in its core. When the helium runs out, the core will contract again. But the Sun isn't massive enough to fuse carbon. So, fusion stops. The core becomes a hot, dense object called a white dwarf. The outer layers, no longer supported by fusion energy, will be blown away into space, forming a planetary nebula. And the Sun's story ends. It will sit as a white dwarf, slowly cooling for trillions of years, gradually fading to black. but that's billions of years in the future. Right now, the Sun is stable, and it will remain stable for our lifetimes and for many millions of years to come. What's strange is that we're here at all. The window of time when Earth is habitable is relatively narrow in the Sun's lifetime. Earth was probably too hot for life in its earliest years due to heavy bombardment and volcanic activity. Life emerged around 3.5 to 4 billion years ago, about 1 billion years after Earth formed. In another billion years, Earth will be too hot for life due to the Sun's increasing brightness. So Earth's habitable period is maybe 5 billion years total out of the Sun's 10 billion year lifetime. And we happen to be living during that narrow window. That's not really surprising when you think about it. We couldn't exist at any other time. But it does remind us that our current situation is temporary. The conditions that make Earth habitable are not permanent features of the solar system. They're temporary circumstances that will change as the Sun evolves. Let's move on to something unexpected. The solar wind. Most people know the Sun emits light and heat. But it also emits matter, a constant stream of charged particles, mostly electrons and protons, flows out from the Sun in all directions at hundreds of miles per second. This is the solar wind. At Earth's distance, the solar wind has a density of about 5 particles per cubic centimeter and travels at around 250 miles per second, or about 400 kilometers per second. That doesn't sound like much. 5 particles per cubic centimeter is far less dense than the best laboratory vacuum we can create on Earth. But the solar wind extends throughout the entire solar system, and over the enormous volume of space it fills, it contains significant mass. The Sun loses about 1.5 million tons of mass per second through the solar wind. That sounds like a lot, and it is. But the Sun is so massive that even at this rate, it would take about 150 billion years to lose just 0.01% of its mass. The solar wind isn't constant. It varies depending on the Sun's activity. During periods of high solar activity, when there are many sunspots and solar flares, the solar wind is stronger and more turbulent. During quiet periods, it's weaker and more steady. The solar wind creates what's called the heliosphere, a bubble of influence around the Sun. Inside this bubble, the solar wind dominates. Outside, the interstellar medium, the thin gas between stars, dominates. The boundary between these two regions is called the heliopause. Voyager 1 became the first human-made object to cross the heliopause in August 2012. It's now in interstellar space, beyond the Sun's direct influence. Voyager 1 crossed the heliopause at about 121 astronomical units from the Sun. That's about 3.5 times farther than Neptune's orbit. The solar system, in terms of the Sun's gravitational influence, extends much farther. The Oort cloud, a theoretical cloud of comets surrounding the solar system, might extend as far as 100,000 astronomical units. But the heliosphere, the region dominated by the solar wind, is much smaller. The solar wind also interacts with planetary atmospheres. On Earth, we're protected by our magnetic field. When the solar wind hits Earth's magnetosphere, it gets deflected around the planet. But some particles spiral down along the magnetic field lines toward the poles. When these particles collide with atoms in Earth's upper atmosphere, they create the aurora, the northern and southern lights. Mars doesn't have a strong magnetic field. So, the solar wind hits Mars's atmosphere directly. Over billions of years, the solar wind has stripped away most of Mars's atmosphere. Early Mars probably had a thicker atmosphere, possibly thick enough to support liquid water on the surface. But without a magnetic field to protect it, the solar wind gradually eroded the atmosphere away. Today, Mars's atmosphere is about 100 times thinner than Earth's. This is one reason Mars is cold and dry today, even though it was probably warmer and wetter billions of years ago. The solar wind isn't just a curiosity. It has practical effects. It can damage satellites, disrupt communications, and even affect power grids on Earth during particularly strong solar storms. In March 1989, a powerful solar storm caused a blackout across Quebec, leaving 6 million people without power for 9 hours. The storm induced currents in power lines and transformers, causing them to fail. As we become more dependent on technology, especially satellites and GPS, we become more vulnerable to solar storms. That's why scientists monitor the sun constantly, watching for signs of increased activity that might produce dangerous solar storms. Now let's talk about the asteroid and comet threat. Most people know that an asteroid impact killed the dinosaurs 66 million years ago. The impact created a crater about 112 miles, or about 180 kilometers, across in what is now the Yucatan Peninsula in Mexico. The explosion released energy equivalent to about 10 billion Hiroshima bombs. It threw vast amounts of dust and debris into the atmosphere, blocking sunlight for months or years. This caused a collapse of the food chain. Plants couldn't photosynthesize. Herbivores starved. Carnivores starved. About 75% of all species on Earth went extinct. But that was 66 million years ago. What are the chances of it happening again? Asteroid impacts are not rare on astronomical timescales. Earth is hit by small asteroids all the time. Most burn up in the atmosphere. Every day, about 100 tons of material from space hits Earth. Most of it is dust and tiny particles. But occasionally, larger objects get through. In February 2013, a meteor about 66 feet, or about 20 meters, across entered Earth's atmosphere over Chelyabinsk, Russia. It exploded in the air with the force of about 30 Hiroshima bombs. The shockwave shattered windows across the region, injuring about 1,500 people. If it had exploded over a major city instead of a rural area, the damage would have been far worse. Chelyabinsk-size impacts happen roughly once every 60 years somewhere on Earth. We got lucky that this one happened over a relatively unpopulated area. Larger impacts are rarer. An impact like the Tunguska event in 1908, which flattened about 770 square miles, or about 2,000 square kilometers, of forest in Siberia, happens roughly once every few hundred years. An impact, like the one that killed the dinosaurs, happens roughly once every 100 million years. These statistics are approximate. Impact rates aren't perfectly regular. Sometimes you go longer between big impacts. Sometimes they come closer together. But, on average, over millions of years, this is roughly how often impacts of different sizes occur. The good news is that we're now actively searching for potentially hazardous asteroids. NASA and other space agencies have catalogued most of the large asteroids that cross Earth's orbit. As of now, we don't know of any large asteroid that will hit Earth in the foreseeable future. The bad news is that smaller asteroids, like the one that exploded over Chelyabinsk, are harder to detect. There are many more of them, and they're smaller and fainter. We probably haven't found most of them yet. And they can still cause significant damage if they hit in the wrong place. The even worse news is that comets are almost impossible to predict. Comets come from the outer solar system, either from the Kuiper belt or the Oort cloud. Most of the time, they're too far away and too faint to detect. We only see them when they fall toward the sun and develop tails from the sun's heat, vaporizing their ice. By the time we detect a comet, it's already on its way in. If a comet happened to be on a collision course with Earth, we might only have months or years of warning. That's probably not enough time to deflect it or evacuate the impact zone if it's large enough. Long-period comets, ones with orbital periods of thousands or millions of years, are particularly dangerous because we can't track them. They're out there in the Oort cloud, too far away to see, and we won't know they're coming until they're already heading toward the inner solar system. But the odds of any individual person being harmed by an asteroid or comet impact are extremely low. You're far more likely to be struck by lightning or hurt in a car accident. Statistically, the risk is tiny. But over long enough timescales, over thousands or millions of years, it's a certainty that Earth will be hit again by large asteroids or comets. And when that happens, the results could be catastrophic for civilization if we're not prepared. That's why there's growing interest in planetary defense, figuring out how to detect and deflect asteroids before they hit. NASA's DART mission, which successfully changed the orbit of an asteroid by crashing a spacecraft into it in September 2022, was a test of this technology. The test worked. We can, in principle, deflect asteroids if we detect them early enough. But detection is the key. We need to find potentially hazardous objects years or decades before they hit, so we have time to plan and execute a deflection mission. Now, let's talk about the Kuiper belt and the dwarf planets. Beyond Neptune lies the Kuiper belt, a region of icy objects left over from the solar system's formation. These objects are similar to asteroids, but are made mostly of ice rather than rock and metal. The Kuiper belt extends from about 30 astronomical units, roughly Neptune's orbit, to about 50 astronomical units. It contains hundreds of thousands of objects larger than 62 miles, or 100 kilometers, across, and possibly trillions of smaller ones. Pluto is the most famous Kuiper belt object. Discovered in 1930, Pluto was considered the 9th planet for 76 years. But in 2006, the International Astronomical Union redefined what a planet is. To be a planet, an object must orbit the Sun, be massive enough that its gravity makes it roughly spherical, and have cleared its orbit of other debris. Pluto meets the first two criteria, but not the third. Its orbit is filled with other Kuiper belt objects. So Pluto was reclassified as a dwarf planet. Many people were upset by this. Pluto had been a planet for as long as anyone alive could remember. Textbooks had to be rewritten. Mnemonics for remembering the planets, "My very educated mother just served us 9 pizzas," had to be changed. But the reclassification made sense scientifically. Pluto is one of many similar objects in the Kuiper belt. Eris, another Kuiper belt object, discovered in 2005, is about the same size as Pluto and possibly slightly more massive. If Pluto is a planet, then Eris should be too. And so should Makemake and Haumea, and probably dozens of other large Kuiper belt objects. Rather than having dozens of planets, astronomers decided to create a new category, dwarf planets, for objects like Pluto. New Horizons spacecraft flew past Pluto in July 2015. The images it sent back were stunning. Pluto turned out to be far more geologically active than anyone expected. It has a heart-shaped region called Tombaugh Regio, named after Clyde Tombaugh, who discovered Pluto. Part of this region is a vast plain of nitrogen ice called Sputnik Planitia. There are mountains made of water ice, some as tall as the Rockies. There's evidence of cryovolcanism, volcanoes that erupt ice instead of lava. Pluto's surface is young in geological terms, less than 100 million years old in some places. That means something is renewing the surface, erasing craters. But what? Pluto is too small to have leftover heat from its formation. It's too far from the Sun to be heated by sunlight. One possibility is that tidal heating from Pluto's largest moon, Charon, provides the energy. Charon is unusually large compared to Pluto. It's about half Pluto's diameter. The two objects are so close in size that they orbit a common center of mass located between them. In a sense, Pluto and Charon are a binary system, two objects orbiting each other. Tidal forces between them might generate enough heat to drive geological activity on Pluto. But we're not certain. Pluto remains mysterious, despite New Horizons flyby. Beyond the Kuiper belt is the scattered disk, a region of objects with highly elliptical and tilted orbits. These objects were probably scattered into their current orbits by gravitational interactions with Neptune. Eris is in the scattered disk. Its orbit takes it as close as 38 astronomical units and as far as 98 astronomical units from the Sun. It takes about 557 years to complete one orbit. And beyond the scattered disk is the hypothetical Oort cloud. We've never directly observed the Oort cloud. It's too far away. Objects in the Oort cloud are too small and too faint to detect with current telescopes. But we infer its existence from the orbits of long-period comets. Long-period comets come from random directions in the sky, not just from the plane of the solar system where the planets orbit. This suggests there's a spherical shell of comets surrounding the solar system. When one of these comets gets perturbed by the gravity of a passing star or the tidal forces of the galaxy itself, it falls toward the Sun. We see it as a comet. The Oort cloud probably extends from a few thousand astronomical units out to maybe 100,000 astronomical units. Its outer edge might be halfway to the nearest star. At these distances, the Sun's gravity is extremely weak. A slight nudge from a passing star could send an Oort cloud object either falling toward the Sun or escaping the solar system entirely. The Oort cloud is probably the solar system's true outer boundary. Beyond it, you're in interstellar space. Now, let's address something most people find disturbing when they learn about it. The solar system is unstable. Not immediately unstable. Not about to fall apart tomorrow or next year or in our lifetimes. But over long enough timescales, billions of years, the planetary orbits are chaotic. Chaos, in this context, doesn't mean random. It means that tiny changes in initial conditions can lead to very different outcomes. The orbits of the planets are determined by their gravitational interactions with each other. You can calculate where Earth will be 1 year from now, very precisely. You can even calculate where it will be 100 years from now, fairly accurately. But try to calculate where it will be 100 million years from now, and the uncertainty grows. Small errors in your measurements of Earth's current position and velocity get amplified over time. After a few tens of millions of years, your predictions become unreliable. This doesn't mean Earth's orbit is wildly unstable. Earth isn't going to suddenly spiral into the sun or get flung out of the solar system. But the exact details of its orbit, the precise shape and orientation, become unpredictable over very long timescales. Computer simulations of the solar system's long-term evolution show that the inner planet's orbits are chaotic. In some simulations, Mercury's orbit becomes so elliptical that it crosses Venus's orbit, leading to a possible collision or near miss that could eject Mercury from the solar system. This happens in about 1% of simulations run forward 5 billion years. So there's about a 1% chance that within the next 5 billion years, something catastrophic happens to Mercury's orbit. Of course, in 5 billion years, the Sun will be a red giant, and Earth will be uninhabitable anyway, so this is somewhat academic. But it illustrates an important point. The solar system is not a perfectly stable clockwork. It's a dynamic system with gravitational interactions that can lead to unpredictable long-term behavior. The outer planets are more stable because they're farther apart and don't interact as strongly. But even their orbits are not perfectly predictable over billions of years. Let's talk about the moons. The solar system has over 200 known moons. Some are tiny, just a few miles across. Others are larger than the planet Mercury. And several are among the most interesting worlds in the solar system. Earth has one large moon, simply called the Moon. It's unusual for a rocky planet to have such a large moon relative to its size. The Moon is about 1/4 Earth's diameter and about 1/80th Earth's mass. This is a much higher ratio than for any other planet-moon system except Pluto-Charon. The leading theory for how the Moon formed is the giant impact hypothesis. About 4.5 billion years ago, shortly after Earth formed, a Mars-sized object called Theia collided with Earth. The impact was so violent that it vaporized both Theia and a large chunk of Earth's outer layers. The debris from this collision went into orbit around Earth. Over time, this debris coalesced to form the Moon. Evidence for this theory includes the Moon's composition, which is similar to Earth's mantle but lacks a large iron core like Earth has. If the Moon formed from Earth's outer layers, this makes sense. Also, the Moon is slowly moving away from Earth. Tidal forces between Earth and the Moon transfer rotational energy from Earth to the Moon, causing the Moon's orbit to gradually expand. The Moon is currently moving away at about 1.5 inches, or about 3.8 centimeters, per year. Billions of years ago, the Moon was much closer. If you go back far enough, it was so close that it would have appeared huge in Earth's sky, perhaps 20 times larger than it appears today. Tides would have been far more extreme. Earth's day was also shorter. The same tidal forces that push the Moon away also slow down Earth's rotation. When the Moon formed, an Earth day was only about 6 hours long. Over billions of years, tidal forces have slowed Earth's rotation to 24 hours. And this process continues. Earth's day is still getting longer, by about 1.7 milliseconds per century. Mars has 2 small moons, Phobos and Deimos. Both are irregularly shaped and probably captured asteroids rather than moons that formed along with Mars. Phobos is slowly spiraling inward toward Mars. In about 50 million years, it will either crash into Mars or break apart from tidal forces. forming a ring around Mars. Jupiter has at least 95 known moons. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610. They're called the Galilean moons. Io is the most volcanically active body in the solar system. Its surface is constantly being renewed by volcanic eruptions. This activity is driven by tidal heating. Io's orbit is elliptical due to gravitational interactions with the other Galilean moons. As Io moves closer to and farther from Jupiter, the tidal forces stretching and squeezing it generate heat. This heat melts rock, creating volcanoes. Europa is covered in water ice. Beneath the ice is probably a global ocean of liquid water, perhaps 62 miles or 100 kilometers deep. This ocean is kept liquid by tidal heating. Europa is one of the best places in the solar system to look for life. The ocean is in contact with a rocky mantle below, providing minerals and possibly volcanic vents like those on Earth's ocean floor where life thrives. NASA is planning a mission called Europa Clipper to study Europa in detail, launching in the next few years. Ganymede is the largest moon in the solar system, larger than the planet Mercury. It's the only moon known to have its own magnetic field. It also probably has a subsurface ocean. Callisto is heavily cratered, indicating an ancient surface. It's the least geologically active of the Galilean moons, but might also have a subsurface ocean. Saturn has at least 146 known moons. Titan, Saturn's largest moon, is the second largest moon in the solar system. It's the only moon with a thick atmosphere. Titan's atmosphere is mostly nitrogen, like Earth's, but it also contains methane. The temperature on Titan is about -290 degrees Fahrenheit, or about -179 degrees Celsius. At this temperature, methane acts like water does on Earth. There are methane lakes and seas on Titan's surface. There's a methane cycle, similar to Earth's water cycle, with methane rain, rivers, and evaporation. Titan might have a subsurface ocean of liquid water beneath its icy crust, similar to Europa. Enceladus, a smaller moon of Saturn, is one of the most exciting discoveries of recent decades. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, discovered that Enceladus has geysers erupting from its south pole. These geysers shoot water vapor and ice particles into space. Chemical analysis of the particles revealed that they contain salts and organic molecules. This strongly suggests that Enceladus has a subsurface ocean of liquid water in contact with a rocky core. The conditions might be suitable for life. Enceladus is now considered one of the highest priority targets for astrobiology. Uranus has 27 known moons. Neptune has 16. Many of these are small and irregularly shaped. But Neptune's largest moon, Triton, is unusual. It orbits Neptune in the opposite direction to Neptune's rotation, a retrograde orbit. This strongly suggests that Triton didn't form with Neptune, but was captured later. It's probably a Kuiper belt object that Neptune's gravity captured billions of years ago. Triton is geologically active. Voyager 2 observed geysers erupting from its surface in 1989. Triton is also spiraling inward toward Neptune. In a few billion years, it will either crash into Neptune or be torn apart by tidal forces, forming a spectacular ring system around Neptune. The moons of the solar system are not just dead rocks orbiting planets. Many of them are dynamic, geologically active worlds with subsurface oceans, volcanoes, and possibly even life. They're among the most interesting destinations for future exploration. Finally, let's talk about what we're still discovering. The solar system is not a static museum. It's an active, evolving system, and we're constantly learning new things about it. In just the past few decades, we've discovered the Kuiper belt, detected thousands of exoplanets that have changed our understanding of how planetary systems form, found evidence of subsurface oceans on multiple moons, and photographed Pluto and Charon up close for the first time. We've sent spacecraft to every planet. We've landed on asteroids and comets. We've captured samples from the solar wind. We've detected gravitational waves and exoplanets and interstellar objects passing through our solar system. In October 2017, astronomers detected an object moving through the solar system on a trajectory that indicated it came from outside, from interstellar space. It was named Oumuamua, Hawaiian for scout or messenger. Oumuamua was elongated, roughly cigar-shaped, and tumbling. Its composition and origin remain mysterious. Some scientists think it was a comet or asteroid ejected from another star system. Others have suggested more exotic possibilities, though the evidence for those remains speculative. In August 2019, another interstellar object, a comet designated 2I, Borisov, passed through the solar system. Unlike Oumuamua, Borisov behaved like a normal comet, developing a tail and showing typical cometary activity. These discoveries tell us that interstellar objects pass through the solar system more often than we thought. We just didn't notice them before, because we weren't looking carefully enough. As our telescopes and surveys improve, we'll probably detect more of them. The solar system is not isolated. It's embedded in a galaxy full of stars, and objects occasionally wander in from elsewhere. We're also beginning to understand that our solar system might not be typical. For decades, we assumed that most planetary systems would look like ours. A few rocky planets close to the star, gas giants farther out, maybe some icy objects beyond that. But observations of exoplanets have shown enormous diversity. Some systems have hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Some have super-Earths, rocky planets larger than Earth, but smaller than Neptune, a type of planet that doesn't exist in our solar system. Some have planets orbiting binary stars. Some have planets with orbits tilted at wild angles. Our solar system, with its relatively circular orbits and clear separation between rocky and gas giant planets, might be unusual. Not necessarily rare, but not the default either. This has implications for the search for life. If Earth-like planets in Earth-like orbits are uncommon, that might explain why we haven't detected any signs of extraterrestrial civilizations yet. Or it might just mean we need to expand our search to include planets that don't look exactly like Earth. The solar system has been our home for all of human history. It's where we evolved, where we developed technology, where we learned to ask questions about the universe. But it's stranger than most people realize. It's not a neat, orderly arrangement of planets, following predictable paths forever. It's a dynamic, chaotic, violent place where planets migrated, moons formed from catastrophic collisions, asteroids and comets constantly bombard the inner worlds, and the sun slowly brightens toward an eventual transformation into a red giant that will destroy everything we know. And yet, within this chaos, there's stability enough for life to emerge and evolve over billions of years. There's regularity enough that we can predict eclipses and planetary positions centuries in advance. There's beauty in the rings of Saturn, in the auroras of Jupiter, in the blue waters of Earth. The solar system is stranger than we thought. And the more we learn, the stranger it gets. Every new discovery raises new questions. Every mission reveals surprises. We thought we understood the planets, and then we found subsurface oceans on moons we assumed were frozen and dead. We thought the planets formed where they are, and then we realized they migrated. We thought the solar system was stable, and then we discovered it's chaotic over long timescales. Science is not about reaching final answers. It's about asking better questions. And our solar system, familiar as it seems, still has countless questions left to answer. Where is Planet 9, if it exists? How common are subsurface oceans on icy moons? Could life exist in Europa's ocean, or Enceladus's or Titan's methane lakes? How did the late heavy bombardment really unfold? What caused the planets to migrate? How many interstellar objects pass through the solar system each year? These questions drive current research. They motivate missions to Europa and Titan and Enceladus. They guide surveys, searching for Planet 9 and tracking near-Earth asteroids. They inspire the next generation of scientists who will continue exploring our cosmic neighborhood. Our solar system is stranger than we thought. But it's also more fascinating, more beautiful, and more full of possibilities than the simplified version we learned in school. It's a place where ice volcanoes erupt on distant moons, where planets wander over billions of years, where ocean worlds might harbor life, where the sun's own evolution will one day transform everything. And it's our home, the only place in the universe where we know life exists. For now, that might change as we explore farther, as we study the moons more carefully, as we search for biosignatures in the atmospheres of exoplanets. But even if we find life elsewhere, Earth will remain special. It's where we started. It's where we learned to look up and wonder. It's where we built telescopes and spacecraft and sent our creations out to explore the darkness. The solar system is stranger than we thought. And understanding that strangeness, embracing it, questioning it, is what makes us human. It's what drives us to explore. It's what makes us look beyond our world and ask what else is out there. The answer, as we're discovering, is far more interesting than we ever imagined. But there's more to this story. Let's go deeper into some of the most unsettling discoveries about our solar system. The solar system's formation itself was far more violent than most people realize. When you look at the orderly arrangement of planets today, it's easy to imagine they assembled smoothly from the disk of gas and dust that surrounded the young sun. But the evidence suggests something far more chaotic. Computer simulations of planetary formation show that the early solar system was crowded with planetary embryos. Dozens or even hundreds of Mars-sized to Earth-sized objects, all orbiting in the same region. These embryos collided with each other repeatedly. Each collision either destroyed both objects, merged them into a larger object, or sent one or both flying into a different orbit. Earth itself is probably the result of multiple giant collisions. The collision that formed the Moon was just one of many. There were probably other collisions before that, other giant impacts that contributed material to the growing Earth. Mars might be small, because it's the survivor of a population of planetary embryos that mostly got swept up by Earth and Venus. It avoided being hit by luck, essentially. The asteroid belt is what's left of a region where planetary embryos never managed to merge into a planet. Jupiter's gravity stirred up the region, increasing collision velocities so that instead of merging, the embryos shattered into smaller pieces. The asteroid belt isn't a failed planet in the sense of a planet that tried to form and couldn't. It's the debris from a region where planet formation was disrupted. This violent history is recorded in the planets themselves. Venus rotates backwards compared to the other planets. Something, probably a massive collision early in its history, flipped Venus over or spun it backward. Uranus is tilted on its side. Its axis of rotation is tilted 98 degrees from the perpendicular to its orbit. This means Uranus essentially rolls around the Sun like a ball rolling along the ground rather than spinning like a top. What caused this? Almost certainly a collision with another large object early in the solar system's history. Mercury has a proportionally huge iron core. Its core makes up about 61% of the planet's volume, much higher than Earth's 45% or Mars's 38%. One theory is that Mercury was once much larger, but a giant collision stripped away most of its rocky mantle, leaving behind a planet that's mostly core. The solar system we see today is the result of billions of years of collisions, near misses, gravitational interactions, and planetary migration. It's not a design system. It's a survivor, shaped by chaos into something that happens to be stable enough to last billions of years. Let's talk about something most people have never heard of: the frost line, also called the snow line. This is a boundary in the early solar system that determined what kinds of planets could form where. Close to the young sun, it was too hot for ice to condense. Only rocky and metallic materials, things with high melting points, could remain solid. This meant that the inner solar system had relatively little solid material to build planets from. Beyond a certain distance, about 3 to 5 astronomical units from the Sun, depending on conditions, it was cold enough for water ice to condense. Ice made up a large fraction of the solid material available. There was more stuff to build planets from. This is why the outer planets are so much more massive than the inner planets. Jupiter and Saturn formed in a region where ice was abundant. They could build large solid cores quickly. Once these cores reached about 10 Earth masses, they became massive enough to gravitationally attract huge amounts of hydrogen and helium gas from the surrounding disk. This is how gas giants form. Earth and the other inner planets couldn't do this. They formed in a region with less solid material, so they never built cores large enough to attract gas. They remained rocky planets. The frost line is why the solar system has its two-part structure: rocky planets inside, gas giants outside. But here's what's interesting. The frost line wasn't stationary. As the young sun evolved, its luminosity changed. The frost line moved inward or outward, depending on how hot the sun was. Also, material in the disk itself moved. Icy particles from beyond the frost line drifted inward over time. Some of them evaporated as they crossed the frost line, releasing water vapor into the inner solar system. Some of this water might have ended up incorporated into Earth and the other inner planets. This is one possible source of Earth's water, though, as mentioned earlier, comets delivered during the late heavy bombardment might have contributed as well. The frost line also affected the composition of asteroids. Asteroids, in the inner part of the asteroid belt, closer to Mars, are mostly rocky. Asteroids, in the outer part, closer to Jupiter, contain more ice and carbon-rich materials. This compositional gradient reflects the temperature gradient in the early solar system. The frost line is a simple concept with profound consequences for how planets form and what kinds of planets you get in different parts of a planetary system. Now let's address one of the most common misconceptions about gravity in the solar system. Most people think the sun's gravity holds the planets in orbit. That's true, but it's incomplete. The planets also pull on each other. And these planet-planet gravitational interactions have important effects. Jupiter, being by far the most massive planet, has the strongest influence. Jupiter's mass is about 318 times Earth's mass. It's more massive than all the other planets combined. When Jupiter moves, its gravity tugs on all the other planets, altering their orbits slightly. Over millions of years, these small tugs add up. This is called orbital resonance, when the orbital periods of two objects have a simple ratio. For example, Neptune and Pluto are in a 3:2 orbital resonance. For every 3 orbits Neptune completes, Pluto completes 2. This resonance is stable. It keeps Pluto's orbit from crossing Neptune's in a way that would lead to a collision or ejection. Even though Pluto's orbit is elliptical enough that it sometimes comes inside Neptune's orbit, the two objects never get close to each other because of the resonance. Many of Jupiter's moons are in orbital resonances with each other. Io, Europa, and Ganymede are in a 4:2:1 resonance called a Laplace resonance. For every 4 orbits Io completes, Europa completes 2, and Ganymede completes 1. This resonance helps maintain the eccentricity of Io's orbit, which drives the tidal heating that makes Io so volcanically active. Orbital resonances can be stable or unstable. The Kirkwood gaps in the asteroid belt are examples of unstable resonances. Asteroids in those orbits get perturbed by Jupiter until they're ejected. But stable resonances, like the one between Neptune and Pluto, can last billions of years. Planet-planet interactions also cause something called secular perturbations. These are slow, periodic changes in orbital elements that don't involve resonances. For example, Earth's orbital eccentricity varies between about 0.0005 and 0.058 over a cycle of about 100,000 years. This variation is driven by gravitational interactions with Jupiter and Saturn. Earth's axial tilt also varies between about 22.1 and 24.5 degrees over a cycle of about 41,000 years. These variations, called Milankovitch cycles, are thought to be one of the drivers of ice ages on Earth. When Earth's orbit is more elliptical and its tilt is larger, seasonal variations in sunlight are more extreme. This can trigger the growth of ice sheets at high latitudes. The fact that gravitational interactions between planets can affect Earth's climate is remarkable. It means that Jupiter and Saturn, hundreds of millions of miles away, have influenced the history of life on Earth. Let's talk about something that sounds simple but isn't. What defines the edge of the solar system? You might think it's obvious. The outermost planet's orbit, right? Neptune orbits at about 30 astronomical units. So that's the edge. But that's not really the edge. There are objects beyond Neptune's orbit. The Kuiper belt extends to about 50 astronomical units. Okay, so that's the edge. But wait. There's the scattered disk beyond that, with objects reaching 100 or more astronomical units. And the Oort cloud extends to maybe 100,000 astronomical units. So, Where's the edge? It depends on what you mean by edge. If you mean the edge of the region where the sun's gravity dominates, where an object orbits the sun rather than being pulled away by the gravity of nearby stars, that's roughly 100,000 astronomical units. Beyond that, the sun's gravity is too weak. A passing star could easily perturb an object into escaping the solar system. If you mean the edge of the heliosphere, the region dominated by the solar wind, that's only about 120 astronomical units, roughly where Voyager 1 crossed into interstellar space. If you mean the edge of the planets, that's 30 astronomical units at Neptune's orbit. If you mean the edge of significant populations of orbiting objects, that's somewhere between 50 and 100,000 astronomical units, depending on whether you count the scattered disk or the Oort cloud. There's no single answer. The solar system doesn't have a sharp edge like a table. It gradually fades out. Objects get sparser, the sun's gravity gets weaker, the solar wind thins, until eventually you can't really say you're in the solar system anymore. You're in the space between stars. This ambiguity isn't just semantic. It reflects a deeper truth about space. There are no sharp boundaries. Everything is continuous, gradual, interconnected. The solar system blends into interstellar space. Interstellar space blends into the galactic environment. The galaxy blends into intergalactic space. It's all one continuous medium, just with different densities and compositions in different regions. Now, let's discuss something that doesn't get enough attention: the role of luck in Earth's habitability. Earth is habitable, not just because it's in the right place or has the right size. It's habitable because of a long series of fortunate circumstances, many of which could easily have been different. Start with the Moon. The giant impact that formed the Moon could have destroyed Earth entirely. If Theia had hit at a slightly different angle or speed, Earth might have been shattered into debris that never recoalesced. We got lucky. The impact was violent enough to create a large moon, but not violent enough to destroy Earth. The Moon itself contributes to Earth's habitability. It stabilizes Earth's axial tilt. Without the Moon, Earth's tilt would vary chaotically over millions of years, possibly swinging from 0 degrees to 85 degrees. This would cause wild climate swings, making it difficult for complex life to evolve. Mars, which has no large moon, has experienced exactly this kind of chaotic tilt variation. Its tilt has varied from 0 to 60 degrees over its history. This probably contributed to Mars losing its atmosphere and water. Earth got lucky by having a large moon. Earth also got lucky with Jupiter. Jupiter's massive gravity acts like a shield, deflecting or capturing many comets and asteroids that would otherwise hit the inner planets. Without Jupiter, Earth would be hit by large impactors much more often. Complex life might never have time to evolve before being wiped out by an impact. Some scientists call Jupiter the solar system's vacuum cleaner. It's not a perfect shield. Some objects still get through, as evidenced by the impact that killed the dinosaurs. But Jupiter reduces the impact rate significantly. Earth got lucky that Jupiter exists and is where it is. If Jupiter had migrated inward, becoming a hot Jupiter like we see in other solar systems, Earth might never have formed at all. Or if it did form, it would be in a much more chaotic environment with frequent close passes by a giant planet. Earth's orbit is also fortunate. It's nearly circular, which means Earth receives relatively constant sunlight throughout the year. If Earth's orbit were more elliptical, seasonal temperature variations would be extreme. One part of the year might be too hot for liquid water, another part too cold. This would make it harder for life to thrive. Earth's composition is fortunate. It has enough radioactive elements in its interior to keep the core hot and molten. This drives plate tectonics and maintains the magnetic field. The magnetic field protects the atmosphere from being stripped away by the solar wind. Without it, Earth might have lost its atmosphere like Mars did. Plate tectonics recycle carbon through the carbonate-silicate cycle, helping regulate Earth's climate over geological timescales. Without plate tectonics, Earth's climate might be less stable. All of these factors, the Moon, Jupiter, the nearly circular orbit, the right composition, are fortunate accidents. None of them were guaranteed. In another solar system, with slightly different initial conditions, any or all of them might be absent. Earth is habitable, partly by design, it's the right distance from the Sun, and partly by luck, everything else happened to work out in our favor. This raises an interesting question. How common are Earth-like planets in truly Earth-like circumstances? We've found thousands of exoplanets. Many of them are in the habitable zone, the region around their star where liquid water could exist on the surface. But how many of those planets have a large stabilizing moon? How many have a Jupiter-like planet in the right place to act as a shield? How many have plate tectonics and a magnetic field? We don't know yet. These factors are hard to detect from light years away, but they might be crucial for habitability. If Earth-like conditions require not just an Earth-sized planet in the habitable zone, but also a specific set of lucky circumstances, then Earth-like worlds might be much rarer than we think. This is sometimes called the rare Earth hypothesis. It's controversial. Some scientists think Earth-like conditions are common. Others think they're rare. We won't know until we've studied more exoplanets in detail, measuring their moons, their planetary system architecture, their magnetic fields. That's decades away, at least with current technology. Let's talk about the Sun's motion through the galaxy. Most people think of the Sun as stationary, with the planets orbiting around it. But the Sun itself is moving. It orbits the center of the Milky Way galaxy, taking about 225 to 250 million years to complete one orbit. This is called a galactic year. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. The Sun is currently about 26,000 light-years from the galactic center, moving at about 500,000 miles per hour, or about 800,000 kilometers per hour, relative to the center. But the Sun's motion isn't a simple circle. It also bobs up and down relative to the galactic plane. The galactic plane is the flat disk where most of the galaxy's stars are located. The Sun oscillates above and below this plane with a period of about 60 to 70 million years. Right now, the Sun is slightly above the galactic plane and moving upward. In about 30 million years, it will reach its maximum height above the plane, about 230 light-years, and then fall back down. This bobbing motion might have effects on Earth. Some scientists have proposed that mass extinctions on Earth correlate with the Sun's position relative to the galactic plane. When the Sun passes through the plane, where the density of stars and interstellar matter is highest, Earth might experience more comet impacts due to gravitational perturbations of the Oort cloud. The evidence for this correlation is debated. Some studies find a weak correlation, others don't. It's possible that the Sun's galactic motion affects Earth's environment, but the effect is probably small compared to other factors like volcanic activity or asteroid impacts. The Sun's motion through the galaxy also means we're constantly moving into new neighborhoods. The stars visible in Earth's night sky are different now than they were 100 million years ago. Stars that were once close neighbors have drifted away. New stars have come close. Over hundreds of millions of years, the constellations change shape. The Big Dipper, for example, looked quite different in the age of dinosaurs and will look different in the distant future. Stars have their own motions through the galaxy. They're not fixed in place. Over long enough timescales, everything moves. Here's something that sounds like science fiction, but is scientifically plausible. Rogue planets. These are planets that don't orbit any star. They've been ejected from their planetary systems and now drift through interstellar space alone. How common are rogue planets? We don't know for sure, but computer simulations of planetary system formation suggest they might be very common. During the chaotic early stages of planetary system formation, gravitational interactions between planets can eject some of them into interstellar space. Some estimates suggest there might be billions or even trillions of rogue planets in the Milky Way galaxy. That might be more rogue planets than stars. These planets would be extremely difficult to detect because they don't have a star illuminating them. They're dark, cold objects drifting through space. A few rogue planets have been detected through a technique called gravitational microlensing. When a rogue planet passes in front of a distant star from our perspective, its gravity bends the star's light, causing the star to briefly brighten. By observing these events, astronomers have detected a handful of rogue planets, but the vast majority remain unseen. Could a rogue planet pass through our solar system? In principle, yes. The solar system is moving through the galaxy, and occasionally it might encounter a rogue planet. The probability is extremely low. Space is vast, and rogue planets, even if numerous, are spread out over such huge volumes that encounters are rare. If a rogue planet did pass through the solar system, the effects would depend on how close it came and how massive it was. A small rogue planet passing through the outer solar system might perturb some Kuiper belt objects, sending a few comets toward the inner solar system. A large rogue planet passing close to the inner solar system could be catastrophic. It could destabilize planetary orbits, eject planets from the solar system, or even collide with a planet. But again, the probability of this is vanishingly small. The solar system has existed for 4.6 billion years, and there's no evidence that it's ever been significantly disrupted by a passing rogue planet. It's possible it will never happen in the remaining lifetime of the Sun. Rogue planets are fascinating to think about. Worlds without suns, drifting in eternal darkness and cold. Some of them might have moons. Some might still have residual internal heat from their formation. It's even conceivable that some could have subsurface oceans kept liquid by tidal heating or radioactive decay. Could life exist on a rogue planet? It seems unlikely. Life as we know it requires energy, and sunlight is the primary energy source for most life on Earth. But life around deep-sea hydrothermal vents on Earth doesn't rely on sunlight. It uses chemical energy from the vents. In principle, life on a rogue planet could use a similar strategy if the planet had enough internal heat to drive geological activity. It's speculative, but not impossible. The universe might be full of dark, lonely worlds harboring strange forms of life in their hidden oceans. We just have no way to find or study them with current technology. let's return to something closer to home: Earth's atmosphere. You probably think of the atmosphere as a permanent feature of Earth, but it's not. Earth has had several different atmospheres over its history. The very first atmosphere, the one present when Earth formed about 4.6 billion years ago, was probably made mostly of hydrogen and helium captured from the surrounding nebula. This atmosphere was quickly lost. Earth's gravity wasn't strong enough to hold on to hydrogen and helium, and the intense solar wind from the young sun blew the atmosphere away. The second atmosphere formed from volcanic outgassing. As Earth's interior heated up and differentiated, volcanoes released gases trapped in the rock. This created an atmosphere of water vapor, carbon dioxide, nitrogen, and other gases. There was almost no oxygen. The early Earth had a reducing atmosphere, meaning it lacked free oxygen. This atmosphere persisted for billions of years. Then, about 2.4 billion years ago, something changed. Cyanobacteria, simple microorganisms capable of photosynthesis, began producing oxygen as a waste product. At first, the oxygen didn't accumulate in the atmosphere. It reacted with iron dissolved in the oceans, forming iron oxide that settled to the ocean floor. This created the banded iron formations we see in ancient rock layers. Eventually, all the available iron was oxidized, and oxygen began accumulating in the atmosphere. This is called the Great Oxidation Event. It was catastrophic for most life at the time. Oxygen is toxic to organisms adapted to a reducing environment. The Great Oxidation Event caused a mass extinction of anaerobic organisms, but it also created opportunities. Oxygen allows for more efficient metabolism. Organisms that could tolerate oxygen and eventually use it for respiration gained an enormous energy advantage. Complex life made of eukaryotic cells with specialized structures, probably couldn't have evolved without oxygen. The Great Oxidation Event made complex life possible. Over the next 2 billion years, oxygen levels rose, eventually reaching the current level of about 21%. This oxygen came entirely from photosynthesis by plants, algae, and cyanobacteria. Without life, Earth would have virtually no oxygen in its atmosphere. It would look more like Mars or Venus. This means Earth's atmosphere is a product of life. Life changed the planet. It created the air we breathe, and Earth's atmosphere is still being maintained by life. If all photosynthesis stopped today, oxygen levels would gradually decline as oxygen reacted with rocks and organic matter. Over millions of years, the atmosphere would return to something more like the pre-Great Oxidation atmosphere, with little or no free oxygen. Earth's atmosphere is not a static thing. It's dynamic, sustained by biological processes, changing over time. The atmosphere we have now is just one snapshot in a long history of atmospheric change. Let's discuss Venus and Mars in more detail because they're Earth's closest planetary neighbors, and they tell us a lot about what can go wrong. Venus is almost Earth's twin in size. It's about 95% of Earth's diameter and about 82% of Earth's mass. It orbits at about 0.72 astronomical units, closer to the Sun than Earth, but not dramatically so. You'd think Venus would be somewhat similar to Earth, maybe hotter because it's closer to the Sun, but still potentially habitable. Instead, Venus is hell. The surface temperature is about 860 degrees Fahrenheit, or about 460 degrees Celsius. Hot enough to melt lead. The atmospheric pressure at the surface is about 90 times Earth's pressure, equivalent to being about 3,000 feet or about 900 meters underwater on Earth. The atmosphere is 96% carbon dioxide with clouds of sulfuric acid. It rains sulfuric acid on Venus, though the rain evaporates before reaching the surface due to the intense heat. What happened? Venus probably started out with conditions not too different from early Earth. It had water, possibly oceans. But being closer to the Sun, Venus received more solar energy. This caused more water to evaporate. Water vapor is a greenhouse gas. It trapped heat, causing temperatures to rise further, causing more evaporation. This is the runaway greenhouse effect. Eventually, all of Venus's water was in the atmosphere as vapor. Ultraviolet light from the Sun broke apart the water molecules into hydrogen and oxygen. The hydrogen, being light, escaped into space. The oxygen reacted with rocks on the surface. Venus lost its water permanently. With no water to dissolve carbon dioxide and sequester it in rocks through the carbonate-silicate cycle, carbon dioxide built up in the atmosphere. Volcanic activity continued to release more carbon dioxide over billions of years. The result is the thick, hot, toxic atmosphere we see today. Venus is a warning. It shows what can happen to an Earth-like planet if conditions are just slightly different. If Earth were a bit closer to the Sun, it might have suffered the same fate. Mars is the opposite case. Mars is smaller than Earth, about half Earth's diameter and about 11% of Earth's mass. It orbits at about 1.52 astronomical units, farther from the Sun than Earth. Mars today is cold and dry. Surface temperatures average about -80 degrees Fahrenheit, or about -63 degrees Celsius. The atmosphere is less than 1% as thick as Earth's, composed mostly of carbon dioxide. There's no liquid water on the surface. Water ice exists at the poles and buried underground, but the low atmospheric pressure means liquid water is unstable. It would quickly evaporate or freeze. But Mars wasn't always like this. Ancient river valleys, lake beds, and possible ocean basins on Mars's surface tell us that liquid water once flowed there. This means Mars must have been warmer and had a thicker atmosphere billions of years ago. What happened? Mars is smaller than Earth, so it cooled faster. Its core solidified, shutting down the dynamo that generated its magnetic field. Without a magnetic field, the solar wind hit Mars's atmosphere directly, gradually stripping it away. Mars also has lower gravity than Earth, making it easier for atmospheric gases to escape. Over billions of years, Mars lost most of its atmosphere. As the atmosphere thinned, surface temperatures dropped. Water froze or was lost to space. Mars became the cold, dry desert we see today. Could Mars be made habitable again? This is called terraforming, and it's a popular idea in science fiction. The basic concept is to release carbon dioxide from Mars's polar ice caps and from rocks, thickening the atmosphere and creating a greenhouse effect to warm the planet. If you could raise temperatures enough, frozen water would melt, creating lakes and possibly seas. You could then introduce plants to produce oxygen. Over centuries or millennia, you might create a breathable atmosphere. The problem is that without a magnetic field, any atmosphere you create will slowly be stripped away by the solar wind. You'd have to continuously replenish it. Also, the amount of carbon dioxide available on Mars might not be enough to create a thick atmosphere. Recent studies suggest that even if you released all the carbon dioxide trapped in Mars's ice and rocks, you'd only get an atmosphere about 1/50th as thick as Earth's. That's probably not enough to make Mars warm and wet. Terraforming Mars might be impossible with current understanding and technology. But that doesn't mean Mars can't be settled. Humans could live in sealed habitats, using resources from Mars to sustain themselves. It just wouldn't be a planet with a breathable atmosphere and liquid water on the surface. Venus and Mars are cautionary tales. They're reminders that Earth's habitability is fragile. Small differences in size or distance from the Sun can lead to radically different outcomes. Venus is too hot, Mars is too cold. Earth is just right, for now. But this Goldilocks situation isn't guaranteed to last forever. Let's talk about Saturn's rings, because they're one of the most beautiful and mysterious features of the solar system. Everyone knows Saturn has rings. But most people don't know how strange they are. Saturn's rings are enormous. The main ring system extends from about 43,000 miles, or about 69,000 kilometers, to about 85,000 miles, or about 137,000 kilometers from Saturn's center. That's a span of about 42,000 miles, or about 68,000 kilometers. But they're incredibly thin. The rings are only about 30 to 300 feet, or about 10 to 100 meters, thick in most places. If you made a scale model where the rings were as thin as a sheet of paper, they'd be about 6 miles, or about 10 kilometers, across. They're the flattest large-scale structures in the solar system. The rings are made mostly of water ice particles, ranging in size from tiny grains to house-sized boulders. These particles orbit Saturn independently, each following its own orbital path. From a distance, they look like a solid structure. Up close, they're a swarm of individual objects. Here's the mystery. The rings are young. We don't know exactly how old they are, but evidence suggests they're only a few 100 million years old, maybe less. That's nothing compared to Saturn's age of 4.6 billion years. Saturn existed for billions of years without rings, and then, relatively recently, the rings appeared. How? One theory is that the rings are the debris from a moon that wandered too close to Saturn and was torn apart by tidal forces. There's a limit called the Roche limit, inside which tidal forces from a planet will tear apart a moon or other object. For Saturn, the Roche limit is about 87,000 miles, or about 140,000 kilometers, from the center. Saturn's rings lie inside this limit. If a moon drifted inward, perhaps due to tidal interactions or a collision with another moon, and crossed the Roche limit, it would break apart. The fragments would spread out into a ring. Another theory is that a comet or asteroid passing too close to Saturn was captured and torn apart. Either way, the rings are temporary. Over time, the ring particles are spiraling slowly inward towards Saturn, pulled by atmospheric drag and other forces. In a few 100 million years, the rings will probably be gone. They'll rain down onto Saturn's atmosphere. This means we're living at a special time. We're seeing Saturn's rings during a brief window in the planet's history when it happens to have them. Billions of years from now, Saturn will be a ringless planet again. Unless another moon or comet gets torn apart and creates new rings, but that's a random event that might or might not happen. Jupiter, Uranus, and Neptune also have rings, but they're much fainter than Saturn's. You need a powerful telescope to see them. These rings are probably made of dust, knocked off small moons by micrometeorite impacts. They're constantly being replenished and constantly being lost, reaching a steady state. But Saturn's rings are different. They're massive, bright, made of large ice particles, and they're temporary. They're a brief, beautiful phase in Saturn's evolution, and we happen to be here to see them. Finally, let's return to the question of whether we're alone. The solar system, strange as it is just one system among hundreds of billions in our galaxy. Each star is a potential sun for its own family of planets. As of now, we've confirmed over 5,000 exoplanets, and surveys suggest that most stars have planets. The galaxy probably contains hundreds of billions of planets. Many of them are in habitable zones. Some are probably rocky like Earth. With so many planets, it seems almost certain that some of them have life. But we haven't found any evidence of life beyond Earth yet. No radio signals from alien civilizations. No biosignatures in exoplanet atmospheres. No artifacts, no probes, no signs that anyone else is out there. This is the Fermi paradox. If life is common, where is everybody? There are many possible answers. Maybe life is common, but intelligent, technological life is rare. Maybe civilizations don't last long enough to spread across the galaxy. Maybe they're out there, but we're not looking in the right way or at the right time. Maybe the galaxy is just too big. Even if there are thousands of civilizations, they might be so far apart that contact is impossible. Or maybe we're alone. Maybe Earth's combination of circumstances, the Moon, Jupiter, the right orbit, plate tectonics, the Great Oxidation Event, billions of years of stability, is so rare that life like ours almost never happens. We don't know. The solar system can't answer this question by itself. But it can tell us what's possible. It shows us that planets are common, that the ingredients for life, water, organic molecules, energy sources are widespread. It shows us that conditions can be stable for billions of years, long enough for life to evolve and become complex. And it shows us that our existence required a long series of fortunate events. Whether those events are common or rare, we don't yet know. But we're looking. Telescopes, like the James Webb Space Telescope, are analyzing the atmospheres of exoplanets, searching for biosignatures, like oxygen and methane, that might indicate life. Future missions will do this in more detail, potentially imaging Earth-like planets directly and studying their surfaces. Within the next few decades, we might know whether life exists elsewhere. Or at least, we'll have much better constraints on how common or rare it is. The solar system is stranger than we thought. But it's also a stepping stone. It's where we learned to ask questions about the universe. It's where we develop the tools to answer those questions. And it's the base from which we're beginning to explore beyond. The more we learn about our solar system, its violence, its chaos, its improbable stability, its temporary moons and rings and atmospheres, the better we understand what's possible, and the better equipped we are to find and recognize other worlds, other systems, maybe even other life. Our solar system is strange, but it's our strange system, and understanding it is the first step toward understanding everything else. Thanks for coming on this journey through our cosmic neighborhood. The solar system we actually live in is nothing like the simple diagrams suggest. It's a place of chaos and order, violence and stability, familiar worlds and alien landscapes. It's a system shaped by billions of years of collisions, migrations, and random chance. It's a system where planets wander, moons harbor oceans, and rings come and go. It's a system where Earth exists in a narrow window of habitability, sustained by a series of fortunate accidents. And it's the only home we've ever known. We're only just beginning to understand it. Now let's talk about comets in much more detail, because they're far more important to the solar system's story than most people realize. Comets are often called dirty snowballs, chunks of ice and rock left over from the solar system's formation. But that description doesn't do them justice. Comets are time capsules. They've been frozen in the outer solar system for 4.6 billion years, preserving materials from the solar nebula in nearly pristine condition. When we study comets, we're studying the raw ingredients that built the planets. There are two main sources of comets in the solar system. Short-period comets, ones with orbital periods less than 200 years, come mostly from the Kuiper belt. These comets have relatively predictable orbits. Halley's Comet is the most famous short-period comet, returning every 75 to 76 years. Long-period comets come from the Oort cloud. Their orbital periods can be thousands, millions, or even tens of millions of years. Many long-period comets are on such elongated orbits that they spend most of their time at enormous distances, only briefly swooping close to the Sun before heading back out. Some comets are on hyperbolic orbits, meaning they're not bound to the Sun at all. They pass through the solar system once and then leave forever. Whether these comets originated in the Oort cloud and were perturbed into escape trajectories, or whether they're interstellar comets from other star systems, is sometimes difficult to determine. When a comet approaches the Sun, solar heat causes the ice to sublimate, turning directly from solid to gas without melting. This creates the coma, a cloud of gas and dust surrounding the nucleus. The nucleus is the solid core of the comet, typically a few miles across. But the coma can expand to hundreds of thousands of miles in diameter. Solar wind and radiation pressure push material away from the coma, creating the tail. Comets actually have two tails. The dust tail is made of small, solid particles pushed away from the comet by the pressure of sunlight. This tail is curved because the particles follow orbital paths as they move away from the comet. The ion tail is made of ionized gas pushed away by the solar wind. This tail points directly away from the Sun, regardless of the comet's direction of motion. On bright comets, both tails can extend for millions of miles. Comet Hale-Bopp, which appeared in 1997, had a tail that stretched across 45 degrees of the sky, about 90 times the apparent diameter of the full moon. Comets lose mass every time they approach the Sun. Ice sublimates, dust is blown away, and the nucleus gets smaller. Eventually, after many passes near the Sun, a comet exhausts its ice and becomes a dead comet, essentially an asteroid. Some asteroids in the inner solar system are probably dead comets that have lost all their volatile materials. Comets occasionally break apart. Comet Shoemaker-Levy 9 broke into multiple fragments when it passed too close to Jupiter in 1992. 2 years later, in July 1994, the fragments crashed into Jupiter in a spectacular series of impacts. Each impact released energy equivalent to millions of megatons of TNT. The impacts created dark scars in Jupiter's atmosphere that were visible for months. This was the first time humans directly observed a collision between two solar system bodies. It was a reminder that impacts aren't just ancient history. They still happen. Comets have hit Earth in the past. The Tunguska event in 1908, which flattened trees across hundreds of square miles of Siberian forest, might have been caused by a small comet or asteroid exploding in the atmosphere. No impact crater was ever found, suggesting the object exploded in the air before hitting the ground. Some scientists think comets delivered much of Earth's water. Comets are rich in water ice. During the late heavy bombardment, billions of comets hit Earth. If each comet contained water, and if enough comets hit Earth, they could have delivered oceans' worth of water. Recent measurements of the deuterium to hydrogen ratio in comets, a kind of isotopic fingerprint, show that some comets match Earth's water while others don't. This suggests Earth's water came from multiple sources. Some from comets, some from asteroids, some perhaps from the original material that formed Earth. Comets also delivered organic molecules to early Earth. Amino acids, the building blocks of proteins, have been found in comet samples. Comets might have seeded Earth with the chemical precursors necessary for life. This is speculative, but it's plausible. The Oort cloud, the source of long-period comets, is one of the least understood parts of the solar system. We've never directly observed it. We infer its existence from the orbits of comets that originate there. The Oort cloud is thought to be a spherical shell of icy objects surrounding the solar system. It's not a disk like the Kuiper belt. It's three-dimensional, encompassing the solar system from all directions. The inner edge might be at a few thousand astronomical units. The outer edge might extend to 100,000 astronomical units or more, roughly halfway to the nearest star. The Oort cloud probably contains trillions of objects. Most are small, comet-sized. But there might be larger objects, even dwarf planets or small planets, lurking in the Oort cloud. If Planet 9 exists, it might be considered an inner Oort cloud object. The Oort cloud formed from planetesimals ejected from the inner solar system during the planet's early chaotic period. When Jupiter and Saturn migrated, they flung countless small icy bodies outward. Most of these bodies escaped the solar system entirely, but some ended up in distant orbits where they were barely bound to the Sun. These are the Oort cloud objects. Over billions of years, gravitational perturbations from passing stars and the tidal force of the galaxy itself have shaped the Oort cloud. Stars occasionally pass within a few light years of the Sun. When they do, their gravity tugs on Oort cloud objects, changing their orbits. Some objects get pulled into the inner solar system, becoming the long-period comets we observe. Some get ejected entirely, becoming interstellar objects. The Oort cloud is constantly being reshaped by external forces. It's not a static structure. It's dynamic, evolving over millions of years as stars pass by and galactic tides pull on it. Let's discuss something that doesn't get talked about enough: the sheer timescales involved in the solar system's evolution. Humans live for decades. Civilizations last for centuries or maybe millennia. Recorded history spans about 5,000 years. Our species, Homo sapiens, has existed for about 300,000 years. But the solar system is 4.6 billion years old. That's about 15,000 times older than our species. It's almost impossible to grasp timescales this long. 1,000,000 years is already beyond human intuition. It's longer than all of human civilization. 1 billion years is 1,000 times longer than that. On these timescales, things that seem permanent are temporary. Mountains erode to dust. Continents drift across the globe and collide, forming new mountain ranges. Species evolve, dominate, and go extinct. Planets change. Mars had rivers and lakes billions of years ago. Now, it's a frozen desert. Earth's atmosphere had no oxygen billions of years ago. Now, it's 21% oxygen. Venus might have had oceans billions of years ago. Now, it's a hellscape. The sun itself changes. It's 30% brighter now than when it formed. In another billion years, it will be bright enough to evaporate Earth's oceans. Nothing is permanent on these timescales. Everything changes. And yet, the laws of physics remain constant. Gravity works the same way today as it did 4 billion years ago. Chemical reactions follow the same rules. The speed of light hasn't changed. This combination of constant laws and changing conditions is what makes the solar system's history so rich and complex. The laws of physics are simple. But when you apply them over billions of years, you get planets migrating, moons forming from collisions, atmospheres evolving, climates changing, life emerging and evolving. Complexity emerges from simplicity over vast timescales. Let's talk about meteorites, because they're pieces of the solar system we can actually hold in our hands. Meteorites are rocks from space that survive passage through Earth's atmosphere and land on the surface. Most meteorites come from asteroids. A few come from Mars or the Moon, blasted off those worlds by ancient impacts. And a very small number might be comet fragments. There are three main types of meteorites. Stony meteorites are made mostly of silicate minerals, similar to rocks on Earth. Iron meteorites are made mostly of metallic iron and nickel. Stony iron meteorites are a mixture of both. The most interesting meteorites, from a scientific perspective, are carbonaceous chondrites. These are primitive, stony meteorites that have barely changed since the solar system formed. They contain tiny round structures called chondrules, which are droplets of molten rock that formed in the early solar nebula. Carbonaceous chondrites also contain organic molecules, including amino acids. Some even contain tiny grains of material that predate the solar system. These pre-solar grains formed in other stars and somehow survived the solar system's formation, getting incorporated into asteroids. By studying pre-solar grains, we can learn about the composition of other stars and the nucleosynthesis processes that created the elements. Iron meteorites are fragments of the cores of differentiated asteroids. These asteroids were once large enough and hot enough that their interiors separated into layers, with heavy metals sinking to the core and lighter rock forming a mantle just like Earth. Later, collisions shattered these asteroids and the fragments became meteorites. When you hold an iron meteorite, you're holding a piece of an asteroid's core, material that was once buried deep inside a world that no longer exists. Martian meteorites are rocks blasted off Mars by impacts and eventually captured by Earth's gravity. We know they're from Mars because trapped gas bubbles inside them match the composition of Mars's atmosphere as measured by landers. These meteorites are incredibly valuable because they're the only samples of Mars we have on Earth. We've studied them intensely, looking for signs of Martian life. In 1996, a team of scientists announced they'd found what might be fossilized bacteria in a Martian meteorite called ALH 84001. The claim was controversial and remains disputed. Most scientists think the features can be explained by non-biological processes. But the possibility that we've already found evidence of Martian life sitting in a meteorite in a lab is tantalizing. Meteorites have been falling to Earth throughout our planet's history. Most burn up completely in the atmosphere. The ones that make it to the ground are usually small, pebble-sized or fist-sized. Large meteorites are rare. The largest meteorite ever found is the Hoba meteorite in Namibia. It weighs about 66 tons and is still sitting where it landed, too heavy to move easily. When large meteorites hit at high speed, they create impact craters. Earth has about 190 confirmed impact craters. Many more have been eroded away or buried over millions of years. The largest confirmed impact crater on Earth is the Rarest crater in South Africa, about 190 miles or about 300 kilometers across. It formed about 2 billion years ago when an object, perhaps 6 miles or 10 kilometers, across hit Earth at high speed. The impact released energy equivalent to millions of nuclear bombs. It would have caused global devastation, possibly affecting the entire biosphere. The Chicxulub crater in Mexico, the one associated with the dinosaur extinction, is smaller, about 112 miles or 180 kilometers across. But it formed more recently, 66 million years ago, when life was more complex and diverse. The extinction it caused was severe. These impacts remind us that Earth is not isolated. It's part of a solar system full of objects moving at high speeds. Occasionally, those objects hit Earth. When they do, the results can be catastrophic. Now, let's discuss solar flares and coronal mass ejections because they're a more serious threat than most people realize. The Sun is not a perfectly smooth, constant ball of light. Its surface is covered with features. Sunspots, dark regions where magnetic fields suppress convection and lower the temperature. Solar flares, sudden releases of energy that brighten a region of the Sun for minutes or hours. Coronal mass ejections, massive eruptions of plasma and magnetic field that blast billions of tons of material into space. These events are driven by the Sun's magnetic field. The Sun's magnetic field is complex and constantly changing. It's generated by the motion of electrically charged plasma inside the Sun. This creates a tangled, writhing mess of magnetic field lines that emerge from the surface, loop through the corona, and sometimes snap and reconnect in explosive ways. Solar flares release energy equivalent to millions of nuclear bombs. They emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. This radiation reaches Earth in about 8 minutes, the time it takes light to travel from the Sun to Earth. When a strong solar flare occurs, it can disrupt radio communications, damage satellites, and increase radiation exposure for astronauts and high-altitude aircraft. Coronal mass ejections are even more dangerous. A CME is a massive cloud of plasma and magnetic field ejected from the Sun. A large CME can contain billions of tons of material moving at millions of miles per hour. When a CME reaches Earth, typically 1 to 3 days after leaving the Sun, it compresses Earth's magnetosphere and can induce electrical currents in power grids, pipelines, and other long conductors. The largest recorded solar storm hit Earth in September 1859. It's called the Carrington event, after astronomer Richard Carrington, who observed the solar flare that triggered it. The resulting geomagnetic storm was so intense that auroras were visible as far south as the Caribbean. Telegraph systems across North America and Europe failed. Some operators reported receiving electric shocks. Some telegraph equipment caught fire, and telegraph messages could be sent even with batteries disconnected, powered entirely by the currents induced by the storm. If a Carrington-level event happened today, the effects would be far more severe. Our civilization depends on electricity, satellites, and communication networks. A powerful geomagnetic storm could damage transformers in power grids, causing widespread blackouts that could last weeks or months. It could disable satellites, disrupting GPS, communications, and weather forecasting. It could damage electronics in cars, computers, and other devices. The economic impact could be trillions of dollars. The social disruption would be immense. This isn't speculation. In March 1989, a much smaller geomagnetic storm caused a blackout across Quebec, leaving 6 million people without power for 9 hours. Transformers failed. The power grid collapsed. It took days to fully restore service. In July 2012, a powerful CME erupted from the Sun. Fortunately, it was directed away from Earth. It missed us by about 1 week. If Earth had been in that position in its orbit, we would have been hit. Studies suggest it would have been a Carrington-level event or worse. The damage could have been catastrophic. We got lucky. Space agencies now monitor the Sun constantly, watching for signs of solar activity. When a CME is detected heading toward Earth, warnings are issued. Power companies can take steps to protect transformers. Satellites can be put into safe mode, but we can't prevent the storm. We can only prepare for it and minimize the damage. The Sun goes through an 11-year cycle of activity. At solar maximum, sunspots and solar flares are common. CMEs are frequent. At solar minimum, the Sun is relatively quiet. We're currently near, or at, solar maximum, which was expected around 2025. This means solar activity is at elevated levels. The probability of a major solar storm hitting Earth is higher during these periods. It's not a matter of if, but when. Eventually, Earth will be hit by another Carrington-level event. The question is whether we'll be prepared. The solar system is stranger than we thought. It's not the orderly, predictable clockwork we once imagined. It's dynamic, chaotic, violent, beautiful, and mysterious. It's shaped by billions of years of collisions, migrations, and chance events. It's filled with worlds more diverse than we ever expected. Ice moons with subsurface oceans. Desert planets with ancient river valleys. Gas giants with storms larger than Earth. Rings that come and go. Comets that rain down from distant clouds. Asteroids shepherded by gravitational resonances. And at the center, a star slowly brightening toward an eventual transformation that will destroy everything we know. But for now, for this brief moment in cosmic history, the solar system is stable enough for life to exist. Stable enough for intelligence to emerge. Stable enough for us to look up, wonder, and try to understand. The more we learn, the stranger it gets. Every mission reveals surprises. Every discovery raises new questions. And that's what makes it fascinating. The solar system isn't a finished story. It's an ongoing investigation. We're part of it, trying to understand our place in this strange, chaotic, beautiful system we call home.